Hello, welcome back to Stat 3050 at the University of Wyoming. We're online, but we're having a great time. So we just finished up looking at linear regression models, simple linear regression models. We looked at the residuals, making sure that our assumptions for linear regression are met. And now we're going to look at confidence intervals and sort of how they're related with p-values. Okay, so what are confidence intervals? Well, typically anything that's estimated can have a confidence interval for the most part. And it really is more or less, and let me get my pen out here. Cool. It's a range of values that you can be some percentage certain contains the true mean of the population. Now, what do I mean by that? Well, in statistics, we have this idea where we go out and we get some sample. And hopefully it's large enough so that it sort of represents at least what is close to the population, right? Because it's very expensive to sample the whole population, right? When it's cheaper to do just one sample, right? Of varying sizes, right? And so we have this idea that, well, okay, with some fancy math, and it's not too fancy, we're able to get a confidence interval saying that between our lower bound and our upper bound, we're able to say that if we were to do this again, or if we were to sample the whole population, there's about a 95% chance that that value that we're estimating, whether it's the slope, whether it's some kind of difference in means, whatever it is, we know that there's a 95% chance that the population value of that estimate is going to be somewhere in that interval. One thing to note, very important, that it's not where 95% of the data lie. That's something else, not totally related. But just knowing that the confidence interval is something that we're using to sort of estimate the true value. But we move on and we sort of see, well, how do these confidence intervals change when we change the level? Well, great question. The default, sort of for us, the convention at least, is using an alpha of 0.05, which results in a confidence level of 0.95, 95%. And we sort of see this is a fairly decent range of values. The statistic that we're estimating is somewhere in here, some sort of estimate, somewhere within this upper bound and lower bound, right? And it's fairly certain that 95% confident that the true population statistic is somewhere in that range. 5%. And then when we put that back into, not percentage, but put it back into decimal form, that's 0.05, which is our alpha. So that's okay. That's good. Just a funky way of showing what the two bounds are. That's all right. And then we see here that we get a fairly decent range of values, right? So sort of going back to our example, this is still of age and muscle density. We see here, I think, if I remember correctly, the intercept was something along the line of, I think, 150 something. Not too worried about the actual value there. And the slope was, I think, about 1.1, right? But this is saying, okay, well, there's a 95% chance that if we were to go out and sample the whole population and do a regression between, age and muscle density for the whole population, that intercept would be somewhere in between these two values. Let me not cross out. Okay, so it would be somewhere between these two values here, right? And then same thing with the age slope, the slope of our beta 1, right? So beta 1 equals, 1.1, negative 1.1 in our model for this sample, but the population slope is probably 95% confidence somewhere in between these two values. And we see they're pretty close together, and there's only a 0.3 some odd difference between the two, which is pretty good. But we also notice that the slope, we know that the p-value was, way less than 0.05, right? It was almost 0. But we notice that 0 is not contained anywhere in here. And we recall that a slope of 0 looks like this, right? So that's good for us. We know that 0 is nowhere in the interval, and that means that our p-value is going to be way less than alpha, which is good, way less than 0.05. But let's say that we wanted to change up the level, and we're changing it to 0.99. So we have a confidence level of 0.99. Well, what's going to happen? I'll let you pause the video for a second, kind of figure out by yourself what's going on. All right, I assume that you took a nice think about this. Hopefully you're not thinking too hard. But we know that as the confidence level increases, so as that increases, the actual interval itself increases. So let me do this. Level, right? Gracefully written. As that increases, the interval itself increases too. So just sort of reminding myself, we're just going to worry about age for now, -1.3 and -1 for the 95%. This would maybe look something more like 1 point, let's see, I don't even remember. Here we go. -1.7 to, who knows, maybe 0.5 or something like that. So still not too bad, right? But it did get a little bit wider. And that's okay, right? This is a total guess. You can run the code yourself and see. It might be different. The lower bound might be different. The upper bound might be different. Both probably are, right? But we know that as the level increases, so does the interval. The interval becomes wider, which is pretty cool. All right. So let's do a quick sort of review on p-values, and let's make sure that we kind of understand how they relate to confidence intervals. So let's look at, I'm going to change this up just to make it a little bit more specific. We're going to look at the beta 1 estimate. And so our null hypothesis, kind of going back to intro stat, our null hypothesis for the estimate, for the slope estimate, is that it equals 0, right? So it would be something like this, that there is no relationship between x and y, right? As x increases, nothing happens to y. And then our alternative hypothesis is that the slope is not 0. So it could be anything else, right? It could be this, which we saw. It could be that, which we did not see. But we just know that it's not 0. And that's what those p-values are relating to. If the confidence interval contains 0, let me use a different color here. If the confidence interval contains 0, then the p-value is going to be greater than 0.05. We know that because if we go back to our interpretation, let's say that we get a confidence interval for our slope, and it's from -1 to 1. And going back to our interpretation of it, we would say there's a 95% chance that if we were to look at the whole population, the slope, or the relationship between x and y, would be between -1 and 1. Well, pretty obviously here, that in the middle is 0, right? So we're saying that there's a 95% chance that the slope could be 0, right? Maybe we didn't observe that, but that just means that our p-value is going to be greater than 0.05 when we're looking at the p-value for the slope coefficient. So just sort of keeping that in mind, one thing directly relates to the other, as far as p-values and confidence intervals go, and it's becoming more popular to report confidence intervals as well. Those are kind of typically a little bit more easy to understand, but that's fine. So p-values and confidence intervals, we know now sort of that they're related in this way. And so let's sort of see how that changes. And so I'm going to put p-value up here too, just so we know. Okay, so confidence intervals, p-values, and the intercept. So let's say we're going to work with our data again, our muscle and muscle density and age, and let's say that we get a p-value for the intercept. That is, so this is a p-value less than 0.05. We know that's what it looks like, right, based on our model in the previous example. But we're going to move on, and let's just say then that the p-value, we do it again for whatever reason, and it's greater than 0.05. Or we have a different study, and the p-value for the intercept, the y-intercept is greater than 0.05. So when we're working in regression, our p-values sort of answer the question, can we trust the estimate? Is the estimate actually what's being reported? Well, oftentimes, when the p-value is greater than 0.05, we know that we can't trust that estimate. So it might look something like this, right? So up here is our intercept, our true intercept, right? But if we were to do it again or have some different data, when the p-value is greater than 0.05, the intercept might be there, it might be there, it could be way up here, we don't know, right? Because we're not able to trust that estimate because the p-value is greater than our alpha. So just sort of keeping that in mind, that's what it looks like. We'll say that the slope is still fine, the slope is still true. This sort of rise over run situation, still all the same, trying to draw it that way. But the intercept we cannot trust. So what about the slope? And I'll write this up here again too so we don't forget. P-values, confidence intervals, and the slope. Well, we know from our past example that the intercept was somewhere up here and the slope looked like that, right? But let's say that the p-value for these other curves are greater than 0.05, greater than our alpha. Not good, right? Not good for us. Let me actually correct myself there. All right. Okay. So let's say then that the slope p-value is greater than 0.05. The intercept is still fine. We'll say that the intercept is up here still. That means that the slope, we cannot trust the estimate of the slope that the model gives us, and the slope might look something like this. It could look something like this, right? Or, more appropriately, it would just look like this, right? No relationship between x and y. And this one right here, this last one here, is typically what we sort of assume when the p-value is greater than 0.05, that there is no relationship between the two variables. So just sort of keeping that in mind. This is exactly what's going on. So there's one other thing before we move on that I want to sort of talk about. And it's the kind of going back to the purpose of regression. Remember, we have two purposes of regression, 2 points, right? One, kind of figuring out how one variable affects the other, x and y, how x affects y, kind of figuring out how that relationship is, how they interact with each other, how one can kind of predict the other, possibly. And then we also use it in terms of predicting unobserved values within our data set, right? So let's say that I have our data over here, right, with these points, and I want to predict, at least sort of estimate, at least what an x value of, let's say right around here would be. We don't have data right there, so we don't know, so we would trace up and over, right? So with this comes, well, great responsibility, but two, a couple of criteria that we need to meet. So if our intercept and, draw like this, and the slope, good Lord, man, very sorry. Intercept and slope have a p-value of, we'll say, for right now, we'll say less than 0.05, less than alpha, less than 0.05. That means we can relate and predict. And if I knew how to spell, we'd be okay. But here we go. And I do. Booyah. So we can relate and we can predict. And I also still do not know how to spell. There we go. Okay. So we can relate and we can predict. But if the intercept has a p-value of greater than 0.05, but the slope is still less than 0.05, then we can only relate, right? That's sort of going back to our initial interpretation of linear regression. As x increases, y increases by, remember, beta 1, whatever that coefficient is, and not the intercept. We don't include the intercept in that change, right? We only look at beta 1. So if the intercept is greater than 0.05, then we don't know exactly where the intercept is. It could be here, it could be here, it could be here, but we know that x still changes in the same way as it does normally, right? So that's okay. Just sort of keeping that in mind. Let me erase this. So maybe take a screenshot or take some notes if you are, which I highly recommend. All right, but just knowing that if the intercept and the slope have a p-value of less than 0.05, both of them, then you can relate, we'll say you can relate x and y. And then you can predict y based on some x, right, and that's all good. If the intercept is greater than 0.05, but the slope is still fine, it's less than 0.05, then you can only relate. You can only relate. You cannot predict with that. So very important depending on what your purpose is. Okay, so we got that covered. That's good. So let's look at confidence bands. Well, what a confidence band is, essentially it's telling you the same thing that confidence intervals do, except it just applies to a whole line. It applies to a whole line. So it looks something like this. And it's just saying that the true line of the population could be somewhere in there, somewhere. And more or less, that's pretty much it. So it could be here, could be here, could be somewhere within that interval, right? Okay, so how does that change? That's the same thing. As you increase the confidence level, you'll notice that the interval gets wider. And it's the same thing. We're more certain that we can get, the bullseye, or at least somewhere around the bullseye with a larger interval. And then the inner here, I've made it a 60% confidence interval, just so you can see sort of the starkness of it. We see that it's very narrow. It's very narrow. And then our normal 95%, it's this middle one here, and it looks good and it looks okay. So we can kind of see that it's all got the same behavior as confidence intervals for a statistic. So, where does that bring us? Well, so that brings us to sort of the end of these PowerPoints. So from now on, as far as big, huge topics, I won't really be making PowerPoints for them. I will be doing them in R instead, because the same rules and the same concepts apply. In multiple regression, it's very similar to simple linear regression. You're just adding more things. And I'll sort of show you along in R how that all works. We'll also be dealing with log transformations and all sorts of different transformations and interpretations for that. And then we're going to be going on to some other more complicated, like polynomial regression and that sort of stuff. And so it really sounds complicated when I'm saying it, but I promise you that as we get into R and into the examples in R, it turns out that it is much simpler. So one thing I would recommend is for you to go through these PowerPoints, these last 3 or so videos that I've made, and just sort of review them. If there's some concept that is confusing, let me know, and we can schedule, time to meet during office hours or whenever. Skype, if you're, not a student watching this, I'm available by email, totally fine. But just know that this is sort of the foundation for everything that we're going to be doing in the future in R. And I still do have a few PowerPoints that go over some sort of major concepts, big major concepts that I want to make sure that we get that are sort of, brought up in IntroStat but then kind of ignored. And I want to make sure that we've got all of that covered. So let's go move over to R, and we're going to get into some examples. I'll see you over there.